All right, so welcome to tonight's high school shared wisdom community. I am JP Thoreau, a member of ICLE's school services faculty, and we have with us. Well, I'll let you both introduce yourselves. Colleen, would you like to?
I'm Colleen Richards from ICLE, Director of School Services.
Luke, I'm the academic dean at St. Mary's High School in Westfield, one of the member schools with ICLE.
Yeah, I'm really excited you could both join tonight. Tonight, what we're going to do is we're going to look at a short selection from Newton's Principia, definitions 1 through 4, and laws 1 through 3 at the very beginning of the work. And so I will right now go ahead and share my screen. All right, and so far we've all had a chance to read this over briefly ahead of time, but what we're going to do now is we'll do a more close reading and discuss as we go. And so the goal for tonight is twofold. It's both to hopefully learn something from Newton and expand our understanding of physics, but then more broadly to also practice and model what it looks like to have a seminar style discussion in a science class for high school. And so the goal for this is really just to see what can be done with this approach. There's a lot of different ways that we can approach our science classes in high school, but I think that a discussion-based class has a lot of value, and hopefully we'll be able to demonstrate that today. So starting off here, why don't we just go one by one here, and we'll start with definition 1, and we'll read it over and then discuss it briefly, and then move on to the next one. So definition 1, I'll go ahead and start off. Quantity of matter is a measure of matter that arises from its density and volume jointly. If the density of air is doubled in a space that is also doubled, there's 4 times as much air, and there's 6 times as much if the space is tripled. The case is the same for snow and powders condensed by compression or liquefaction, and also for all bodies that are condensed in various ways by any causes whatsoever. For the present, I am not taking into account any medium, if there should be any, freely pervading the interstices between the parts of bodies. Furthermore, I mean this quantity whenever I use the term body or mass in the following pages. It can always be known from a body's weight, for by making very accurate experiments with pendulums, I have found it to be proportional to the weight, as will be shown below. So there's a lot packed into that first definition. What are we, first of all, what is being defined here in definition 1?
Quantity of matter, like the amount, if we were going to put a number on it, right? How we calculate that?
Good, so quantity of matter. I'll go ahead and use this highlighter here for this work. Good, and so you said, Luke, if we would calculate it, what other factors go into calculating it?
Density and volume of the same matter.
Okay.
I'm slightly curious about his sense of arises from here. If what he means is, density and volume are the numbers we need to calculate quantity, that seems straightforward enough. But, is this like one and the other cause the third, in which case, I'm suddenly very uneasy with what that means arises from. And is that a sense of causes or just calculation?
Yeah, that's a great question. And it seems like the definition here is not being overly specific as to exactly what that means, right? Arises from. He does give the example here following the definition, so maybe that will help elucidate what he means.
Right, because he's talking about 4 times as much and 6 times as much. So now he's getting into some numbers. And I recognize the density formula, like sort of there in those words that he has.
Yeah, can you say more about that, Colleen?
Well, I mean, just pulling from, I don't know, something I learned in science class, isn't it? Density equals the amount of matter per the unit of volume, mass per unit of volume. So that's what this makes me think of, but he doesn't state that precisely, does he?
So if we say, oops, that was not what I wanted to do, was it? Try that again. If we say density equals right, that's what you're
Sure.
saying, Colleen. Now, if we, and this is bringing in a little bit of outside knowledge, but I think it may be helpful just to figure out what he's saying right now. So if we take that classic equation there and let's move it around, right? And let's put volume on the left-hand side, right? Then we have mass equals volume times density, right?
Mm-hmm. Right.
In which case the formula, Colleen, you have and the statement he has are just restatements of the same. We're not
Well, that's
deriving one from the other. We're just rearranging the same claim, right?
I didn't quite check it yet. So if density is doubled, there is 4 times as much air. Oh, and the space is also doubled, the volume. Then yeah, the quantity of matter, as he says, would be multiplied by 4. That is true.
And he, to be clear here, he says, I mean this quantity whenever I use the term body or mass. So we're being fair here and just using the word mass for these equations, I think.
Mm-hmm. 6 times as much of the space is tripled. Yeah, the time does fit into the equation. If you put the mass is times 6, and that's what he said, right? And there's 6 times as much if the space is tripled. Yes.
It's interesting that he needs to specify any medium and how that doesn't count, right? A medium pervading the interstices between the parts of bodies. I look at what he said up above about condensing powder or condensing snow, and I'm not really clear on how much you can condense a powder other than getting the air out. So I understand how that would be relevant, but I'm
Well,
a little less than clear on what condensing them other than removing a medium is, or is he just stipulating it? Like, I don't mean the medium as part of the mass of the thing because it's of a different, kind of material.
and the air would be the medium, right? And you take the air out and you can form a brick, kind of like
Okay.
those peat pots that you make plant seeds in.
Okay. Or if we were, say, using his snow and we were going to make bricks for an igloo, right? Same idea. You're taking a very powdery, airy snow and removing all the medium. So I guess then we have to understand that his density here would mean if you took the snow before it's packed in, and you'd have to find a way to measure just the snow without the air inside it for this to hold. Because he's not weighing, well, weighing is the wrong word. He's not calculating on the air as part of the snow, even though it's mixed in.
Right, but less dense snow has to have something else there, I guess, unless it's just a vacuum. If you took the air out, you would have more dense snow. wouldn't you?
You say that last part again, Colleen.
If you imagine that powdery snow, and if you were to remove the air, you would end up having more dense snow. Or if somehow you could have powdery snow with no air and still
Right.
same space. I don't know.
Yeah, and these are great. Yeah, these are great questions. I'm wondering if this is why he is choosing the specific phrase, I am not taking into account
Oh,
any medium.
yeah, maybe.
So basically
as
ignore
in-
the air and then everything is true about the snow or powder.
Yeah, it's almost like I just don't want to talk about that, right? I don't want to talk about what else is in the jar of snow, right? Besides the jar and the snow, right? And whether there's air in there, whether there's some other medium, right? Whether we've created a vacuum here, right?
Mhm.
I'm not taking that into account. I think he's trying to avoid these kind of questions because I think you're right that these are in themselves kind of thought-provoking questions.
Kind of isolate the thing.
Yeah,
Leave out those interfering factors.
yeah. I that's my sense. Yeah,
In which case, not taking into account might not mean quite not want to talk about, but that's not going to tally up in my sum and my formula here.
yeah, right. For the sake of this definition, we'll leave that aside, right? Yeah.
Mhm.
Do you want to move ahead to the next one, and we can always circle back here.
Mhm.
Anyone want to read this one aloud?
I'll go.
Yeah.
Quantity of motion is a measure of motion that arises from the velocity and the quantity of matter jointly. The motion of a whole is the sum of the motions of the individual parts. And thus, if a body is twice as large as another and has equal velocity, there is twice as much motion. And if it has twice the velocity, there is 4 times as much motion.
So quantity of motion, we're talking about distance. Quantity is a measure of motion that arises from velocity or speed, and quantity of matter, definition 1, mass. So he's saying distance is velocity times the mass. Is that what he's saying?
I don't think it's distance.
Quantity of motion.
I think he means something other than distance, though, because what he says is the motion. At the end, if it has twice the velocity, or sorry, equal velocity and twice as large, right? So if something that's this much mass is moving and something twice as big is moving at the same speed, there's twice as much movement here. I don't know if we have a common word for this, but more stuff is moving and therefore there is more movement here, even if observably they're the same pace. Is that the sense of it?
If there's more movement, wouldn't
Yeah, more stuff is moving.
more stuff is moving, but the stuff is the mass, right?
And therefore more movement is happening. Is that the sense of quantity of motion we're looking for here?
Yeah. And
more movement occurring.
Right. I think, yeah, more movement occurring, right? Then so that arises both from, right, what do we have? It arises from both from velocity and quantity of matter, which we just saw is synonymous with mass, right?
Yeah, it would help if we had a common word for this, right? I'm comfortable with density. That's an ordinary word, but quantity
Right.
of motion is not a phrase I throw around. And I don't have a vocabulary word to stick on that concept.
I do. It's distance.
Okay.
But I don't know. Is that right? Quantity of motion.
Well, let's.
I guess it could be like a vibration kind of thing. That's a lot of motion, but it
Let's do this because for the sake of modeling the discussion, I would really like to just inject a term in here, but I think it would, but the whole point of this is not to, the whole point of this demonstration right now is not so much to make great strides in Newtonian physics as much as it is to, right, show what we can do with the discussion method in a science class, right? So yes, there is, I think you're right, both of you, that there is a term for this. What we might be able to do is figure out what the attributes of this term would be without necessarily having the word for it, right? So thinking about, right, quantity of motion, right? And I think Luke, you said a minute ago, it's just how much motion is there, right? We're looking both at the speed of the thing and its mass, right? So what if he doesn't give any examples here, but what if we just take a couple examples and think about, well, let's start with this, right? This arises from phrase that we saw in the previous one. We just interpreted that as density times volume, and that seemed to line up. So what if we just do that with this as well, right? And we say, okay, let's say velocity, right, times matter equals question mark, right?
Quantity of motion.
Yeah, quantity of motion,
which is our
whatever.
indeterminate term.
Right.
Oh, I think now that I'm seeing it in formulas, this scientific term is coming to me.
I'm going to change that to mass. There we go. Velocity times mass, right? Right. Yeah, the scientific term might be.
I think I've remembered the term here.
Yeah. It might start to dawn on you here. Let's think of an example. So let's think of two things moving really fast.
Let's roll a golf ball and a bowling ball down a bowling alley.
Okay.
That sounds like a good, I don't know, image, right? It's more than double, but still.
Right, sure. Okay, so we have two things, and let's say the golf ball and the bowling ball are moving the same speed. Okay, they have the same velocity, but one has more mass than the other, right? Which one would you, if you were a bowling pin?
Oh dear, I no longer like this example.
Imagine what it's like to be a bowling pin. That's gonna be our caption for this post here. Imagine what it's like to be a bowling pin. What would you rather get hit with, the golf ball or the bowling ball?
The golf ball, because of how much force it has.
Yeah, so the golf ball is going to hit you with a greater amount of force, right? And
with lesser, right?
Sorry, thank you. The golf ball is going to hit you with less amount of force than the bowling ball, right? And even if we postulate that they're both moving at the same velocity, right? It's because the bowling ball has a greater amount of mass.
Mm-hmm.
So this is a matter of momentum, then, right? I think this is the term I was looking for.
Momentum is, yep. That is the term that we commonly use today for this quantity of motion. Is momentum. Right. So the bowling ball going down the lane has a greater amount of momentum.
So the only reason this definition clicked for me is it drew an analogy for me from something else for my reading. And Colleen, I think you and I have joked about this, that almost all and only of my science reading is from reading recipes and food scientists. One of the earliest things I learned in cooking is heat is not the same as temperature, because a very thin, lightweight frying pan at, say, 600 degrees and a very big, heavy cast iron one are going to deliver very, very different amounts of heat. You know this because you'd rather, I don't know, you'd rather not lean against something stone when it's very cold out, right? The fact that there's more mass there means that the same temperature as the air communicates much more cold. So that mass times some other quantity is how hot something is. But that analogy seems to hold here, right? It's the velocity instead of temperature times the amount of stuff. But yes, this is why we love cast iron and why I'd rather be hit by the golf ball.
For the
Velocities
volleyball,
being equal.
yeah. So I don't know. I think that's, and again, just to kind of break the fourth wall here a little bit, right? This would be a way that I would recommend approaching discussions, right, on these primary source texts is you want to make the connections to your textbook glossary of terms, right? I mean, you do, right? But I think it's a lot more helpful to allow the students to work through what are we actually talking about here, right? And really kind of tease out the implications of what this, this unknown term is, right? And then when you get there, you can say, by the way, we have a word for that. This is the word, right? And if you approach it that way, it seems to me that you're allowing the students to do a lot more of the work on the front end to understand the concept rather than just giving them a term to memorize and of course promptly forget if you do it the other way, right? So that's kind of what we're modeling here right now as we're going through the text. Definition 3. Any takers on definition 3?
Read the whole thing through. Stop me if you think you need to stop.
Okay, yeah, that sounds good.
Inherent force of matter is the power of resisting by which every body, so far as it is able, perseveres in its state either of resting or of moving uniformly straight forward. This force is always proportional to the body and does not differ in any way from the inertia of the mass, except in the manner in which it is conceived. Because of the inertia of matter, every body is only with difficulty put out of its state either of resting or of moving. Consequently, inherent force may also be called by the very significant name of force of inertia. Moreover, a body exerts this force only during a change of its state, caused by another force impressed upon it. And this exercise of force is, depending on the viewpoint, both resistance and impetus. Resistance, insofar as the body, in order to maintain its state, strives against the impressed force, and impetus, insofar as the same body, yielding only with difficulty to the force of a resisting obstacle, endeavors to change the state of that obstacle. Resistance is commonly attributed to resting bodies and impetus to moving bodies, but motion and rest, in the popular sense of the terms, are distinguished from each other only by point of view, and bodies commonly regarded as being at rest are not always truly at rest.
Thank you. All right, so there's a lot there. Why don't we just start with the stuff that was super clear to us, and then we can kind of check off those boxes and move to the more difficult stuff.
I don't understand why he feels the need to stipulate a new term, inherent force of matter, if it does not differ in any way from inertia.
Luke, you did the exact opposite of what I wanted you to do. You started with the confusing thing instead of the easy thing.
I thought that was the straightforward terminology. The whole
that's great. Luke's like, no, this was the clearest part of this definition. It still made no sense. Oh man, that's great. Yeah, no, that's fine. Let's just go with that. Let's go with that. So yeah, point us to the line here.
He starts by defining inherent force of matter, and then about 2 lines in, he says, This does not differ in any way from the inertia of the mass,
Yeah.
except in the manner in which it is conceived. Is there something wrong with conceiving of it as inertia?
Well, maybe what's implied here is that the conception of inertia is like, gosh, is that other view where, because he's saying it depends on your viewpoint.
Okay.
Where does he say it? Down below.
Yeah. So down at the bottom.
This exercise of force is, depending on the viewpoint, both resistance and impetus. It's
Yeah.
resistance this way.
Yeah, that to
Yeah.
me was where it got confusing.
And maybe
Yeah.
his description of it depends on your viewpoint is different from the inertia thing, the way it is commonly conceived at his time, because he hasn't really, it's the first time he's using this word in this text, or at least this passage.
Resistance
In
is
the popular sense of the terms, maybe
Right.
the popular sense of the terms, that's the inertia.
So he might be deprogramming or unpacking a presumption we're not bringing into the text.
I think so.
So maybe I don't need to worry about so much about the semantics in the beginning as the lack of distinction between movement and rest at the end.
Yeah. Why don't we look at that? I think that's going to be, because I think what Colleen's saying is if we get to the end, we see what he actually wants us to think, as opposed to what he's afraid we might think, I think.
Motion and rest in the popular sense of the terms are distinguished from each other only by point of view. I find myself at first blush slightly suspicious of that claim.
So this is this is where the art of grammar, right, is kind of sneaking its way into our science class, because look at the modifier here is interesting, right? Motion and rest in the popular sense of the terms are distinguished from each other only by point of view. He's saying in the motion and rest, right, these terms as popularly understood are actually only distinguished from each other by this point of view, right? So I don't think he's saying that motion and rest are popularly only distinguished by point of view. I think he's saying that the way people understand motion, the way people use the terms motion and rest in popular conversation are really just distinct by point of view.
What most people mean by motion and what most people mean by rest are distinguished by point of view. Not that motion and rest are actually,
the things that people mean when they say motion and when they say rest are really the same thing, distinct only according to point of view, I think is what he's saying.
So. I don't think so, because the first part of the sentence seems very clear. Resistance is commonly attributed to resting bodies and impetus to moving bodies. That's the common notion.
Mm-hmm.
Motion and rest in the popular sense in the terms, meaning referring back to the first part of the sentence.
Yeah.
Are distinguished from each other. I think this is what he's trying to say. He's trying to establish as different from the common understanding, are distinguished from each other only by point of view. I think that part is where he's articulating what is commonly understood, that resistance is what resting bodies do and impetus is what moving bodies.
Yeah. So he's saying that's what's commonly understood. And then how do you understand what he actually thinks here?
But motion and rest in the popular sense of the terms, but
yeah,
that actually are distinguished from each other only by point of view. So I think what he's saying is that the resistance is actually a force of some kind.
Yeah.
And the impetus is a resistance of some kind. That
Yeah.
those words almost are interchangeable.
Yeah. So I think you and I are saying the same thing. I think you're saying it more clearly than I was. But yeah, I think we're understanding it in the same way. Can we illustrate this with an example that might help?
That's what I was working on, and I
Yeah.
think I have one that's gonna get it.
Okay.
JP, if you and I are on a train,
Yep.
on the same train,
Mm-hmm.
and you're sitting across from me, as far as I'm concerned, you're at rest. We're staying the same distance apart from each other.
Mm-hmm.
But to Colleen, who's not on the train, who's standing there watching it go by, you're moving very, very fast. Does that get at the point of view he's talking about? Is JP resting or is JP moving? Colleen and I would disagree, I think.
I don't think that's it. I was thinking more like something like a tug of war, where where something's being pulled and something's well, everyone's pulling, I guess you could say in that case. But the side that is really trying to hold their ground, it is actually really pulling. They're doing their best to pull.
And we have, sorry, go ahead.
Yeah.
I was gonna say we have an example very, very like that in this reading, actually.
Yeah, is it the rock and the horse?
Yeah, just to support the way you're reading this, I think there's basis in the text for that. And this is moving ahead a little bit, but we don't have a whole lot of time left, so might as well just keep.
This was down in Law 3, right?
Yeah.
The equal and opposite forces, the horse dragging the stone.
Right.
Yeah, so that as the horse is presumably winning, because I'm imagining a small stone. So the horse is dragging the stone, but the stone is pulling on the horse. So where we would look at that commonly and say, oh, the horse is pulling the stone, but you could look at it from the other point of view and say, well, the stone is pulling on the horse as well. And depending on how large the stone is, maybe the stone wins. Maybe the horse can't pull it, even though he's not intentional or moving muscles or something.
Yeah, and I don't really know what to say about either of these two examples. I mean, they both seem relevant, I guess. And certainly your example, Colleen, right now, that's literally in the text. I do wonder if this part here, right, bodies commonly regarded as being at rest are not always truly at rest. I mean, I wondered what he had in mind when saying that, and my immediate thought was like, well, he must know that the earth is moving, and even if somebody's standing, even if you have a giant building on the earth, right, Rock of Gibraltar is actually not at rest, right? So I don't know. So I'm definitely kind of open to both of these examples as being useful here for looking at this.
I wonder is another way of like in the beginning he said, disregarding the medium and all that stuff. Like, I don't want to talk about all that stuff right now. I wonder if this line is another one of those.
Yeah.
Bodies commonly regarded as being at rest are not always truly at rest. You mentioned a tug of war, Colleen. If you and I were in tug of war and happened to be perfectly equally matched, anyone looking at us would be like, oh, look at this like nice stable equilibrium and look at these resting figures. And you and I are gonna be sweating and grunting and pulling, right? And I don't feel like I'm at rest here, but it looks that way.
Yeah. That's really good. Yeah.
Yeah. Is that at rest here mean more like not exerting force than not moving then?
I don't know.
Yeah, let's see, going back, right? It says, yeah, it says, yeah, I think this may be the key sentence here. A body exerts this force only during a change of its state caused by another force impressed upon it. And this exercise of force is, depending on the viewpoint, both resistance and impetus. Do you want, can I just give a bit of a spoiler here, just because we're running out of time? This is going to be, I think what you're saying with the tug of war example, I think it is I think it is more or less what he's thinking. This concept here is going to come into play with planetary motion, right? And so and what we have here is just the really initial setup for basically how he, you know, creates calculus, right, to study the motion of planets. And so essentially the kind of the idea that's going to come out of this is basically you can look at any given point on a planetary orbit, and at any given point, right, you have the planet is moving in a direction, right? And say the force of gravity just stopped, right? Stopped exerting itself. The planet would shoot off into space in a straight line, right? But at any given point, the force of gravity from let's say the sun is pulling on that planet, right? And so at any given moment in the planetary orbit, you have this going on, right? Where you have another force, right, being impressed upon it, right? The force of gravity from the sun is being impressed upon the planet, and vice versa, right? And so long story short, though, I think it's somewhat analogous to your tug of war example, in the sense that when you see a planet moving in a circle or in an ellipse, right, you wouldn't think of it as constantly being tugged, right, by the sun. It just looks like a very peaceful circle, right? But
Okay.
but by this understanding of the way it's working is actually every single moment the sun is tugging on the planet, right? Tugging, right? And so your tug of war example, I thought, actually kind of tied in with that, pun intended.
Well, and
See
and
what you did there.
the parallelogram down in one of those laws kind of shows that. Like,
Yeah, let's go to that, because I really wanted to get to that as a kind of a cherry on top here for what we're doing tonight. And so maybe just a PSA announcement right now. We are sadly not going to be able to get into the laws very much, but why don't we just read through each one of them, just the italics, right? Let's read through the italics just so we know what we're dealing with, and then let's move on to the parallelogram proof, and then if we have to go back to check something, we can. So the first one, law one: every body preserves in its state of being at rest or of moving uniformly straight forward, except insofar as is compelled to change its state by forces impressed. Law two: a change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. And then law three: to any action, there's always an opposite and equal reaction. In other words, the actions of two bodies upon each other are always equal and always opposite in direction. So in a more perfect scenario, we would have time to talk about those in depth, but we know they're there, so we can go back to them if we need to right now. But let's look at this corollary and see what's going on with this this parallelogram. All right, so he says a body acted upon by two forces acting jointly describes the diagonal of a parallelogram in the same time in which it would describe the sides if the forces were acting separately. All right, so before we look at this proof here, what are the sides of the parallelogram representing?
The two forces acting on the body.
Okay, good. So the two forces acting on the body. And so then the diagonal of the parallelogram, what's that representing?
Where the body
the actual movement of the body acted upon, right?
Right. So basically what we're looking at then is we're looking at we're looking at the actual movement, right? But then we're breaking it up into components, right? On the two adjoining sides of the parallelogram, right? So okay, so that's kind of our scenario. And so then he's saying, so what's he want to prove about this scenario? So you have a body being acted upon by two forces at the same time.
Mm-hmm.
Does what?
It forms like this combo force.
Right.
So the body actually does something that's in the middle.
Yeah. So the body does something in the middle, and in terms of the actual compound motion here, right? What does he say happens with that motion in terms of time, right? What does he say about the time?
Right. Will make no change at all in the velocity.
Same time. Oh, you're right. Okay, so I was looking at the parallelogram and thinking about that in terms of distance, but no, in the same time. So it's covering basically a shorter distance, meaning AD is less than AB and BD combined, right? As a sum in the same amount of time.
Yeah, that's right. That's right. So let's look at what he says here then. So let a body in a given time by force M alone impressed in A. So the one wonderful thing about this diagram is neither force M nor force N are included in the diagram, right? So I have to figure out what's happening there, but we do have a body at A, right? So I think A is our
start.
Yeah, so that's our, let's just call A our planet for the sake of conversation here. So A is our planet, and by force M is carried with uniform motion from A to B. So I think what we're looking at is A moves this way
Mm-hmm.
according to force M.
Mm-hmm.
Okay.
And then similarly, by force N from A to C.
Mm-hmm.
And I don't know if my technology will allow, imagine an N with arrows pointing that way. All right.
If you're thinking of this in terms of planetary motion, something like one of the two forces is the momentum of the planet as it would move in a straight line, and the
Yep.
other force, gravitational pull.
Yep. I think
So
that's
here C is like the sun, and A is your
let's
planet going from B
let's
to B.
roll with that. Let's say C is the sun.
Okay,
Um,
I like the color
that's a
coding.
great, that's I think a helpful visual here, right? So A is our planet, right? With this, the velocity that it would, or excuse me, the velocity would be going had the sun not exerted a force upon it, right? And so as a result, instead of going in the straight line to B, it ends up taking a turn here along AD and ending up here instead.
Yeah.
Cool.
Is that, are we comfortable with that's what he's saying?
Well, I'm comfortable with it in the diagram, thinking of it just in terms of these lines, but it gets more complicated if it's actually a planet, because at every instant, as you say, the two.
Yeah. Right.
It's not
Right.
really a D.
Yeah. No, that's absolutely right. So this is, and so what's really fascinating about this, and this, if hate to just give a teaser here, but this is like just step one, right, in getting to what you're describing, Colleen, right, in terms of looking at, okay, so we get this figured out, right, then we eventually build up to building a model, right, with a series of deviations and parallelograms around those deviations, right, and the more points you put on your polygon, right, it approaches a curve, right, the limit approaches a curve, right, and so this is the beginning of your calculus right here.
And now it starts to feel like calculus, right? If you put an infinitely large number of incrementally closer and closer together parallelograms, your AD turns out to be a circle or a curve.
Yep.
Got it.
And so
that's pre-calc, right?
Let me here, just if this will, here's my Newton. This is the book that I got this from. Here we go. You can see my diagram. That this is, we're kind of moving in this. This is where we start going shortly afterwards, right? We start getting things like this, right? And so you get basically a polygon, right, with many sided polygon, and again, the more vertices, right, you get, eventually it approaches a curve, right? And so you can, so this is where it all starts right here.
This must be just the beginning, because based only on what we have, we couldn't develop an orbit that isn't a circle. But I know enough outside science to know there are ellipses. So really kind of want to dig into how that happens then.
Well,
how is it stable if it's elliptical?
Can I recommend to you this book?
some light reading for my spare time.
Even better. Here's the citation right here, so you can just get the authoritative translation. Is the one I'm working with.
I thought it was older than 2016. How funny.
Yeah, that was what easybib.com told me, is this printing was from 2016, but the translation's from 1999. So, I don't know what to say. But
I mean, we could go interdisciplinary, and who needs a translation? It's be much more fun in the original.
Yeah. Much more fun.
Well, this little conversation shines a good little light on my unfortunate experience in calculus, both in high school and college, and so that's good. Thank you.
Oh well, we neither of you said for the sake of posterity here, right? How many times had you read Newton before this?
Oh, I never read Newton before.
There you go. Right. So this is. And so this is kind of what we really wanted to demonstrate this today, was you can really do a lot, right? You can do something very meaningful, right? Even with a group of students who have never read Newton before, right? Just by looking at the text directly, right, and having a discussion on it, right? Because I know, as you know, I've been a math teacher myself for years, and I know kind of the tendency is to want to, you know, use the textbook as much as you can. And in fact, I actually did teach Newton for during one school year as well. And so when I had this opportunity, I was serving as a long-term sub, right? And they had me fill in for the physics class, and they said, here, just teach Newton, just right out of the book. And I was like, no way, no way. Like, and this is what opened my eyes. It was like, yeah, the high school students, right, had never seen Newton before, and they were just diving right in. They were diving right in, and we were having these kinds of conversations on the text, and not just, you know, this for the sake of shared wisdom community tonight. We did the very early, right, definitions and laws here, but with the high school students I was working with, we got way into it, and some really complex props and proofs, and you know, so again, just really what I hope we demonstrated tonight was just the real power and just the joy of having a discussion, right? A discussion on a text in a seminar format, and really just how much you can get out of it, and really allows you to kind of dig deeper and ask those important questions that Newton himself was struggling with, right?
Yeah.
Well, any final thoughts before we stop the recording here?
This was great. Thank you.
Thank you.
All right. Well, yeah, thank you so much, and for coming, and then yeah, just really we have shared wisdom community once a month, and I'm really looking forward to more throughout the year, and you know, would love to invite all of our premier member schools. Faculty from all our premier member schools are welcome to join us, and it's a real highlight of my month. So thanks again for coming.
Thanks, JT. Good to see you, Luke.
Thank you. Good to see you.